So I'm going to talk about moonbounce. If you have any questions, because I know a lot of you are not hams, and usually I give this talk for people who are radio amateurs and telling them how to become as radio amateurs to make use of the moon as a way of communicating to distant places. And I talk about that. That's the way this is structured. But if you're not a radio amateur, you'll still get an introduction, a flavor of something that's really exciting. And that is that here on Earth, you can send a signal up and touch the moon and have that signal actually come back and hear it and receive it. And most people find that really exciting. The fact that we can touch something in space and come back and actually control or see those effects. So let me talk about the introduction to this talk. And this is basically what I'm going to do is I'm going to talk a little bit about moonbounce, what I'm doing right now. I'm going to talk about the history, why EME, why it's a technical challenge for those who are radio amateurs or anybody, okay? Talk about how to do it. And I'll probably go over it, spend less time on this and arrange some other time when I have a higher technical audience that can, appreciate the more technical stuff. So how it's done and what you need, I'm going to try and go over quickly and then conclude and open up for questions, because there's a lot of interesting questions that come out of this. Okay, so it's one of the first things is interesting is that how EME, and I use that word, that stands for Earth, Moon. You send your signal to the moon, Earth. The signal, that's where EME comes from. So your signal from the Earth, you're sending the signal. I can use this diagram over here to the moon. The signal gets reflected off the moon, just like you hear an echo. You have a big wall and you say hello, and the echo hits the wall and comes back to you, except the moon's a little further away than the wall there. And it's interesting, it's as someone who teaches about electronics, electrical engineering, how many things happened here in New Jersey? I probably should ask how many New Jerseyites are here. I'm biased toward New Jersey. A few of us here. I was born in New Jersey, lived in New Jersey basically all my life. And it's amazing, truly amazing, how many things were invented in New Jersey, not just in electronics, but in general, like the first submarine was done in New Jersey. And we get to electronics, the first everything was almost, it seems like that, was done in New Jersey. And the first accepted radio signals bounced off the moon basically was not basically, it was done here in New Jersey. Now there were reports of reception of echoes before this, where people had observed that they heard something that looked like it was coming from the moon. They couldn't explain why this echo, but there was nothing really scientific, definitive in terms of, we're going to set this up and we're going to show that we receive these signals off the moon and gather scientific data. That first occurred here. It occurred not too far away, over toward Red Bank or New Jersey, Brick, that area there. Place we used to be called Fort Monmouth, but it wasn't really at Fort Monmouth. Close by, it was in the Evans, they call the Evans area, where they had a big antenna there, which was then very close to the amateur, we referred to as the 2-meter band. Those of you that are hams for radio amateurs, but at that time the 2-meter band didn't exist. Before World War II, there was the 2.5-meter band. It was around 115 megahertz, and that's where the experiments were done. The person who was in charge of the experiments, a lot of the people there were all radio amateurs. So moonbounce has had this thread of amateur radio in it, even from the very beginning. Now, there was another set of experiments that occurred almost in parallel with the experiments that we did, which I found always very fascinating, I should say. And these experiments were done in Hungary. A group in Hungary, and it was done at a frequency that was lower than 2 meters, but they set up an antenna, more of a wire type of antenna. And what they did is they had a transmitter, and they would turn the transmitter on, they would send the signal to the moon, and then they would listen for that signal coming back from the moon. Now, because of the frequency they operate at, the power, they couldn't detect that signal. But what they did is they repeated this again and again and again, and they listened to, every time they did it, they had another switch here. And here I'm getting a little bit technical. Am I okay?
Yeah.
I don't know. You should tell me. I think I'm okay.
Yeah, looks like you're
Okay here in the room. Okay. Am I okay? No, I'm not okay. So what they did is they used this thing that basically stored charge. So if the signal was strong, they would store a piece of that charge in it. We call these things capacitors, if any of you had physics or in high school or things like that. And they'd switch. So it was like kind of digital. They switch from one capacitor 1 second, other capacitor next second, and they switch around. Turns out that echoes from the moon has a certain distance. Radio signals or electromagnetic waves travel at the speed of light. So they go at a fixed amount. So we can predict when we're going to have an echo from the moon, because we know how far the moon is away. And it turns out it's about 2.5 seconds. So if they're doing this and they're looking at the charge or the voltage that's on the capacitor that's 2.5 seconds, right? After this should have a big peak on that. And that's exactly what happens. If you do this with a radar system, you send a pulse out in the radar signal, you'll see 2.5 seconds later, you should have a big peak. They, of course, are making use of what we call integration, repeated transmissions, and they're adding these up. The signals that are random noise, they're going to average out to 0, but where the signal comes back, it's going to add, and it adds up. And if they do this enough times, they get a peak. And they also show, it was about the same time. You can argue about who did it first, because they really took months, literally months, when they were doing this to do this experiment. But they also showed that you positively got signals from the moon. Now, one of the fascinating things, because I remember when I was first reading about this, I think I was in high school or, on that age, and I was trying to figure out what they were doing, because they talked about using hydrogen jars. Okay. Now, anyone in high school remember high school? Not that long ago. Any of you take chemistry in high school? Okay. What did you do with hydrogen? Did you do any experiments with hydrogen? No way. You probably know. You do any experiments? Anyone do experiments in high school with hydrogen? Remember the hydrolysis of hydrogen? I certainly would think about. Yeah, they would take and put 2 electrodes in water, and the water would separate out the hydrogen and oxygen. Water is H2O. Remember that? H2O now. Yeah. We have a right chemistry professor teacher on that, but they would do that. Okay. Well, this group basically did the same thing. At each one of these points where they have each one of these, suppose I call them capacitors, they had a hydrolysis, a couple jars, where the electrodes went into the water, and then they collected the gases that came off of that. Okay. And then they showed that they had the most hydrogen and oxygen at the jar where they were 2.5 seconds later. You see, that seems like they have these things called Rube Goldberg experiments in the feeding devices. Why would they want to do that? These guys in Dallas, I'm sure they had a team there. They were pretty smart. The problem back when they were doing this in the 40s is that capacitors don't hold their charge over a long time. They were doing this over weeks and months, and the capacitors that had available would start to leak, lose the voltage they have. But when you do hydrolysis, the gas doesn't go away, it stays. So they got around the problem of the leakage that you have in the capacitor side. And that's why they did it. I always found that because it shows from an engineering point of view, engineering is really solving problems. And these people who did this, developed this experiment, they figured out how to solve the problem of detecting radio signals that came back from the moon, and with very limited facilities to do it, like a hydrogen jar, some long wires, a limited transmitter, and they were able to show it. Here in the US, we had a big antenna, high power transmitter. In either case, we showed that signals were coming back from the moon. Okay, now from an amateur point of view, because remember I'm talking about amateurs, not the government. And even though the amateurs were there in the government, amateurs were also very early interested in this thing, really very early on. I mean, literally, as soon as the people announced that they were getting echoes from the moon, amateurs said, can we use this to communicate further? One of the things that amateur radio is interested in always is to do something first, to do something over longer distances. And at that time in particular, that people could not communicate very far at the higher frequencies. You have the short wave bands where the signals bounce off the ionosphere. As you go higher in frequency, the really people want to do something different. You go higher in frequency. People wanted to talk further and further, but they couldn't talk very far because the signals basically went right through the atmosphere. It turns out there's some other effects. I had more time here to talk about different types of VHF propagations. But in fact, in those days, if you worked 50 miles, people were going, I worked 50 miles. That's fantastic. So they were looking at ways they could talk further, communicate further. And if you send a signal to the moon and the signal's reflected back to the moon, you can literally, any place they can see the moon and where the signal's reflected back, you can communicate. So you can communicate all over the world at these very high frequencies where normally you can only talk a few miles. And so that's where the interest was in amateur radio, because they wanted to communicate with further places, have the record for the longest distance. The most stations worked all over the world. These are the things that amateur radio operators play at. That's the games that they play at. And echoes were first reported by amateur radio operators. 1946 was when the signals were first reported here in New Jersey. In 1953, we had a group, and also that group was in New Jersey, interestingly, just a coincidence, who reported having echoes from the moon in 1953. But there are certain rules when you communicate, and you got to send the signal. It's got to be heard. The signal's got to be sent back. We call this thing a QSO, two-way communications. And to make a contact or a QSO in amateur radio, you got to meet these rules of being able to have the signal received, sending information back that is unknown at the other side, confirming that you got that information, and having it going back the other way. And the group that was playing around with EME back in 1953 never made a QSO. Okay? In fact, people questioned that was being done at the 2-meter amateur radio band, which existed after World War II, 2-meter amateur radio band. One of the most popular radio bands in the world today is 2 meters. You see all these handy talkies, and you're taking the classes, you end up with a 2-meter transverter and things like that. It's inexpensive equipment all around. So this was the band where this was going on. The first two-way communications occurred in 1960. It was between Massachusetts and California. On the frequency was 1296 megahertz. So that's about 10 times the frequency of 2 meters. They did it, and it was I was involved in this, and I again, I don't want to spend too much time, but when I was in high school, I got interested in building antennas, these what was called a stress dish, and that brought me interest in EME, and I actually built a stress dish when I was in high school, which was damaged when my first day in college. We had a hurricane. And again, I don't want to go into the details, but I've been interested in this from going back. I graduated in high school. I shouldn't say this, tells you how old I am, but in 1960, the same year that that two-way EME communications was achieved. And I was, at that time, there was a fellow by the name of Sam Harris. And for the younger groups over here, he was writing a magazine column every month, and he was like my idol, it really incredible fellow, and at that time, and his wife was also involved, Helen Harris, in amateur radio. So it wasn't just an all male thing even back then. I remember her call was W1HOY. Anyhow, that was a very exciting time in 1960. And I got involved with this, not to blow my horn or anything, but in 1976, I was the first person to communicate with all continents by EME. I did that up at 432 megahertz. There was a group at 144, so I always felt really good because I beat out the 144. I did it at a higher frequency than the predominant lower frequency band, which was supposedly easier to do in 1976. And I got a lot of publicity from it, a lot of fun. And I've been involved with EME since that time. And so this gives you kind of a time frame. And you go higher in frequency, we talk about the wavelength. The antennas get smaller and smaller and smaller. At high frequencies, for those of you who aren't in amateur radio, you're talking about antennas that are in feet. Like one of the most popular bands for shortwave amateur radio is 20 meters. And 20 meters, you know how long that is because you know how long a meter is, so over 3.5 feet, right? So if we say it's like 3 feet, 20 meters, the wavelength there is about 60 feet, okay? To give you a comparison. When you talk about 432, that's 500 megahertz, and the wavelength is a couple feet, okay? About a couple feet in size. So you're going from 60 feet to a couple feet in size. And by the time you get to 10 gigahertz, this is you're getting up into the real microwave frequencies. A wavelength is 3 centimeters. It's about that long. That's the wavelength. So you think about the difference. The equipment, the circuitry, everything becomes very sensitive to distance. And they push the limits of this up to 47 gigahertz. So that's almost 5 times higher. So it'd be 1/5 of that 3 centimeters in 2002. And there really hasn't been a lot of progress since then. There's some interest in 87 gigahertz, but there's really not been full two-way communications yet in that frequency range. Okay, so that gives you a little background, and I got to look at my time because I'm famous for running over time. I think I'm over here. This period ends at anyone know when I end? 3:30. Okay, so I got to get done well before that. There, don't let me go over. If I was in a class, I'd be sure. You know, when you're in a class and you get close to the ending time, you hear this rustling. This background noise, you know you don't need a clock. You know that your time is over, no matter how exciting or what you're talking about or how important it is. Anyhow, talking about exciting, why moonbounce? It's exciting, and even if you're a non-ham, it's exciting. This concept of sending signals off the moon. In amateur radio, people like to collect work rare countries. You know, you come home and say to your wife, you know, I worked India today, and she says, oh, that's nice, what else is there? But this is a lot of what amateurs radio is involved with, whether you're at high frequencies. One of the most competitive fields in high frequencies is collecting work in different countries. When you have people who go out to islands that are little rocks and they spend $100,000 chartering a boat, getting a helicopter to get out there, setting their equipment up, and they work 50,000 people. Literally, I'm not exaggerating. Those of you who operate at HF know I'm not exaggerating. There's great deal of interest because they want to get one more country to their list and stay at the top of the XCC list. Well, this kind of mentality has gone up in the frequencies, and people are interested in the higher frequencies of working all around the world, collecting countries. I'm one of the fortunate people to have the XCC, which stands for working 100 different countries at 70 centimeters and 1296. And I wasn't first, but I was in the top 3 in those categories of working different countries. And it's really competitive and interesting. And it's also interesting because you can go to different places and I've certainly done that. I've done my own traveling and set up equipment portable. This shows a picture of me at home with equipment. This shows me actually in St. Thomas, the Virgin Islands, where I had a business trip and I went out and we set up an antenna to work bound signals off the moon and work people there a few years ago. So if you're an amateur, it's by going on moonbounce, it's a way, if you operate at these higher microwave or VHF frequencies, it's a way of you adding more places and getting more awards if you collect them for working different distances. And we look at the challenge. This talks about the technical challenge of working moonbounce, and that you need, obviously, just like I showed you in the beginning, you need a transmitter, a receiver. You transmit the signal up to the moon, and then if you're listening for echoes, about 2.5 seconds later, you flip this to the receive side. You go and listen and see if you can hear the echoes coming back from the moon. If you're communicating with a station, you send whatever your communications, you send out a call for that station. Is identifier, is call letters, just like my call letters are K2UYH on my hat here. And the other station hears my signal being sent up to the moon. He knows that when he stops hearing me, it's going to take 2.5 seconds for him to respond to me, because he responds immediately. There's a 2.5 seconds, the time getting up there. And then if he immediately responds, it's going to take the other half of that time. It's really 2.5 seconds round trip for me to hear him coming back. Can't occur instantaneously. And we could talk a lot about this, because the person speaking here before was talking about space communications and things like that. And some of the issues in space communication and using satellites and using the moon is the delay in communicating up to a satellite or the moon, which is further away than most of the satellites are, and getting back to it, that delay. And it's very interesting. I could go on and talk about that, because you hear these things about drones, right? You know about a drone? Everyone knows what a drone is, right? Well, someone's piloting that drone usually, right? But the signal has to get from the pilot to the drone. Usually that goes through a satellite to the drone, and the control signal gets back. So that drone really has to do a lot of stuff on its own. And when you start talking about doing robots in space, the 2.5 seconds to the moon is pretty, how should I say, benign, short, compared to if you're trying to control a robot around Jupiter, you're talking about 8 minutes or so, the signal just to get there. So it's going to be 8 and 8 or 16 minutes to get back. So this all gets into it. There's also an issue of what we call path loss. And I'm not going to spend some time in equations here, but there's a huge amount of path loss. Now, again, I love to talk about physics and why things happen. And people think that there's loss in sending electromagnetic waves into space. The truth is there's none. There's no loss. When you send a signal out into space, it's lossless. This is why we can see light from these, quasi-stellar objects that are, not millions, but billions of light years away, because there's really no attenuation in space. Space doesn't attenuate electromagnetic waves. So you say, why do electromagnetic waves get weaker? Anyone know why electromagnetic waves get weaker? No, this is what I'm saying. The atmosphere, well, there is a loss to our atmosphere, but fortunately our atmosphere is thin. And if you go up in frequency, our atmosphere becomes transparent. You go lower in frequency, this waves spread out. Exactly. Think about it. When you got a flashlight, you can see that flashlight being spread out. And the further away you are, the more spread out it is. And if you've got a finite size of the antenna, or finite size in your eyeball, right? It's finite size. You only pick up a small percentage. The further away you are, the less percentage you get. In fact, that's related to what's called square law. In physics, everything, a lot of things seem to be square law, and it's really just the signal spreading out. And so as you go twice the distance away, you only get 1/4 of the energy because it's spread out on you. And the further you go, the less energy that you get. So that's where this path loss comes from. And these numbers that I have here are very large because the signal goes out, it's spread, it hits the moon, about 6% of the energy comes back off the moon. And that has to do with the material the moon is out, how smooth it is, how flat it is, but roughly 6%. But then that signal now is spread out again when it comes back. So it's spreading out when it goes the opposite way. And it's worse than if you went twice the distance. Twice the distance, you're already collimated. Now, hit the moon, though it's not a point, it still causes a respreading of the signal. Like you're starting out at a point, but it affects it and it lowers the loss. So it's like having a signal that you send out and then you resend the energy you have out again. So the spreading is a lot worse than if you went twice the distance to the moon, which is what you're doing to the moon and back. So you get more path loss. Anyhow, there's huge path loss. And this is a great thing if you like a challenge, because it means the signal is really small. And according to this, the higher in frequency you go, it looks like the signal is weaker, but it isn't actually weaker because the path loss equation is built on this concept of having a finite sizing antenna. And when you go up in frequency, the antenna gets smaller. So the antenna intercepts less energy. So your path loss appears to go back up. If you have two antennas or two systems that are the same size, as you go up in frequency, you maintain that size, like with a dish. You have a dish antenna on receive and transmit. It's a so many foot dish. As you go higher in frequencies, it's still that same number diameter dish, right? So it intercepts the same amount of energy. You find out that your path loss actually gets less, interestingly, as you go higher in frequency, because you're intercepting the same amount of energy on the receive side, but on the transmit side, the beam becomes smaller. I don't want to spend too much time on it. As I say, I like talking about physics, and you'll see that a very interesting experiment to take is take the sun and make up a pinhole, like a pinhole camera. Make a pinhole to a sheet of paper. The sun is all collimated in red. So the rays are parallel by the time you get here. They go to the pinhole, they start spreading out. Okay, and the amount of spreading depends on the diameter of the pinhole. The pinhole is very big, you don't see any spreading. As the pinhole gets smaller, you get spreading. So the gain, this is directly related to the gain of an antenna. The gain of the antenna comes from the fact that it's concentrating the energy. It's not sending the energy in all directions. And that's directly related to the size of the radiating structure. And the higher in frequency, when you look at this, the narrower beam is on the transmitting side, but on the receive side, you still receive the same amount of energy. So as you go higher in frequency, there's less path loss. So there's advantages to going higher in frequency. Now, there are other practical limitations, but let me go on. I don't want to, as I said, I didn't want to get too complicated here, too involved. We can talk about the technical challenge. You want the biggest antenna you can possibly have. This happens to be a picture of the antenna I have in my house. I've had that up for about 50 years, since 1973. Amazing that it hasn't fallen on me yet, but it's still there. You want to make, that was the largest antenna I could get my hands on back then. Actually came from Bell Labs. They were cutting it up, and I went there with a bunch of students, and we moved it back to my house, and then we figured out how to mount it. You want the highest power, obviously, you can have. Now, as an amateurs, we're limited by laws to how high a power we have, but as you go higher in frequency, it does become more difficult to generate those high powers technically. And oops, I skipped over something here. You want to have as sensitive a receiver as possible. And it turns out, now I'm going to get technical here, that when you receive a signal, okay, the thing that limits you is the noise that's present, okay? Because if the signal is higher the noise, then you can hear it. But if the signal is lower than the noise, you can't. And so what you want to do is you want to have the lowest noise contribution you have. Now, part of that noise is contributed by what comes in from space. This, in your antenna, your signal's coming in the antenna, noise from space is coming in your antenna, and that's frequency dependent. Turns out that someplace from around 500 megahertz up to around, starting in gigahertz to around 10 gigahertz, and even a little higher, there's very little noise contributed. This is really noise, cosmic noise, noise that comes in from radio stars, things like that. And there's very little noise contributed. It's like that, referred to as a radio window. So your noise coming in the antenna, there's some, but it's relatively low. The most of the noise contributed by what you use to amplify the signal. And what you want to do is design that receiver so it contributes as little noise as you possibly can. And again, this is a topic we could get into. Radio astronomers pull their receivers down to almost absolute zero because it turns out that noise depends on temperature. And the higher the temperature something's at, the more the electrons move around. Second law of thermodynamics, the more noise you get. So you want to get the lowest possible noise contribution. Excuse me. Yeah, KT. I usually say KTB. Boltzmann's constant. You'll get that in physics. The temperature that you're at, and the bandwidth you're listening over. Now that you have some control over, but it's the reason if you're sending a lot of information, you have to have a lot of bandwidth to do that in. And what does it take? And I just say, if you want to be a big gun, you got to do all of this. You can even talk in terms of single sideband, but most of the operation today on moonbounce is being done digitally. People have developed digital software. One fellow in particular also is in New Jersey, interestingly a lot, by the name of Joe Taylor, one of my neighbors, literally. And he has a Nobel Prize, but when he's not working on his Nobel Prize in physics, he spends time developing software for radio amateurs. And he's developed the whole technique to digitally communicate that gives you effectively very, very narrow bandwidth communicate, and can become very efficient, more efficient than even using your ears. And the gold standard was Morse code. You send Morse code, you make the signal very narrow. You can listen to us, people are very good. But if you use digital processing techniques today, you can even beat what you do with a Morse code reception, which, as it had used to be, the gold standard of receiving the signals. And much of the EME operation today, a large percentage of it, is done using these digital techniques at this particular time. But there's still people who like doing things the hard way. You're always going to have that. And the hard way can be a challenge that will make contacts via CW. And I should say, hams know does anyone know? A lot of you don't know what I mean by CW. CW is the thing that you hear da, 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 with a key. That's called CW. And it may sound strange. Why is it called CW? And it goes back historically, when they first started to send radio signals, they send them by a technique called spark. They discovered that when you have a spark jump between two pieces, produce the spark, and the spark generated radio waves. And it was all waves. But that's Marconi was. He was producing the spark type transmitter, and he used some filtering, but it was basically all frequencies coming out of the transmitter. It was a very noisy phenomenon. And that's how radio began, using spark transmission. And until people realized that if you could send a sinusoidal wave, this continuous tone, and that's where it comes from, CW, continuous wave, you're sending a nice continuous sinusoidal signal, and this occupies essentially zero frequency. So you have a very narrow band signal, which means in your equation ATB, you're going to use a very narrow bandwidth. You find that the limitation becomes one really of your ears and hearing and things like that, not the exact filter that you have. So that became the dominant way of communicating. But initially, when radio began, people were done using the spark, which really sent the spark. It's like the spark wasn't going continuously sparking on and off, produced this noise that you see, that was the signal. And then when they figure out how to make this thing as a continuous wave, then it became CW. And that term has stayed with us, even though it's not obvious. What does someone mean by CW today? You know, continuous. I got to change it. I got to turn it on and off. And so there's a lot of different ways to do this. And I'm talking here because I'm trying to get people interested in this and saying how little an antenna that you need to make contacts off the moon. And I'm saying here that when I started out at the 1296 megahertz band, which is a wavelength of about like that. It's 30 centimeters actually, or close to it. That I started experimenting with Joe Taylor's digital, and I was amazed that it didn't take very much to work someone. Here is an example of one of the first stations I worked. I first using digital techniques, and this was with a fellow OH3MCK. That's his call letters. He was in Finland. Okay, come on, and he was using 40 watts, where I was using like 1,000 watts or so, close to that, to make that contact, and it becomes much easier. And I'm just going to give you some example. This is a relatively small antenna here, and of course, when I ask questions, I say, where do you think this is happening in my class? And of course, the answer to the question is usually right on the screen, right? So this obviously happened in the South Pole. This fellow was down there as an experimenter, not in radio, but down at the South Pole, and he brought his radio equipment with him, and he put the South Pole on the 1296 band. So it's another country, another continent, Antarctica for people. And that used this little antenna that he stuck out in the snow, literally, and was down there. This fellow was a German explorer. And I'm just showing you what's needed. Here is an antenna from a fellow in Belarus, and he's got his antenna on his balcony. He's got a 1.2 meter dish, and actually he was making contacts on CW, because I don't like to say that you have to just do things the easy way or the easier way. You can also work some of these smaller stations using the old-fashioned way with Morse code, or even single sideband in some cases. And I should correct myself there. You're saying, what do I mean by single sideband? And how many people know? Eva knows what I
don't know. I had a question. Could you explain at some point before you ended about the lunar lander?
Well, what do you want to know about the lunar lander?
Maybe you explain general population terms, because there's a lot of people about this lunar.
Well, I it's hard for me to answer that question. Let me finish this up and I'll come back, and I'm going to try and speed up here and finish up. We're not too bad, but I got to be done in a few minutes if I keep on top of this. And I'm going to continue just showing you small antennas. This is actually a TV antenna that someone's developed or applied, and shows that you can work these very small antennas off the moon, so you don't have to invest in big antennas. This is a friend of mine. He was a college student at the time this picture was made, and he traveled around, and he had this relatively long antenna. He broke it up and carried it in his car, and he traveled around Europe and set up. He is right now in this picture in Monaco, So he drove Monaco, no one was around, drove there late at night so he could set up right in the center of the town. Took his antenna out, stuck it on a pole he could lash it to, and went on and worked a bunch of people from Monaco. I was worried that he might get stopped or something by the police, and he did that. It went all over the place, and rarer places. Actually, I should go. If I can go back, I was going to go back, and this over here, the picture over him is him setting the same thing up, pulling the same trick in San Marino. He doesn't do as much now. He got married, and all these are antennas are all at 23 centimeters. Okay, it's the 1296 amateur band. It's a bit above 1 gigahertz. 1.3 gigahertz would be if you think about a gigahertz is 1,000 megahertz for everyone here, and and I even got involved with this. This shows me right over here when I was operating in Bermuda. And my approach was not to use a Yagi, but to use, I've always got involved since high school in these stress dishes. So that's a small stress dish that I used where I was in the parking lot behind the hotel near their motor scooter building. This is just a thing to hold umbrellas. So that's where I put my antenna up, and this is the antenna. The whole thing was, carry-on type luggage. We took the whole station there, and you can see my wife is cooperative sometimes moving this. So there's all sorts of fun things you can do. We've done a number of different countries using this. I'm just going to show you these just other examples of small antennas that people that have used. We're not talking, this is a meter, right? So we're talking about antennas that are, are reasonably small size that you can make up and work. Here's another one. This one is being used. We got higher in frequency. Higher in frequency you go, the smaller the antennas you can get by with. But from most radio amateurs, it's relatively easy to get on 1296 today. Equipment is readily available. And my message here is you don't need a really big antenna to go out and start making contacts and working all around the world. Though I'm showing other options. This slide is really can only probably be appreciated by people who are active in amateur radio. This shows a Yagi antenna, those things with those little wires coming out. This is for 3 centimeters. So you can't see it there, but the active elements with little tiny little things, they're on a little stand. And they're making this Yagi antenna work at 3 centimeters. And you see signals off the moon. Just kind of close up of the antenna. As you can see more of what it is. And this is a station in Australia. He's worked a lot of different places, and he's used the Yagi antenna to receive signals up there, though most of the time he uses a dish, I must say. This is another example of a small antenna. This one over here is a 0.5 meter, but this was demonstrated at one of the conferences I was at, and he was showing you could use this 0.5 meter antenna to receive a beacon station. That's a station that's continuously transmitting a signal off the moon, even though this is only a 0.5 meter in size. So there are a lot of possibilities. Now I'm going to jump over this. This talks about digital basics. Some of the things that should catch your eye here is W1JR, Joe Taylor. He's the one who started this whole thing off and came up with this very popular system. By the way, interesting, we talk about amateur radio today, that this started out in the RF and microwave frequencies, but JT, digital communications, because it's so easy to do, has taken over HF. And I'd say the majority of HF today is now being done. When I say HF, this is the shortwave bands where people spend their time. It's easy to work using the atmosphere or long distances. but they've adapted using digital techniques too, because they're just interested in getting this new country. And if they can do it digitally easier than using CW or voice, it has become very, very popular. And I'm just here getting into some of the practical aspects of operating digital, what the screen looks like, and the information you have, and that you can make this thing work. This is there are different technologies that are used depending on the frequency that you're operating at. And this is a mode that was developed for very, very high frequency, and it shows a signal station that I worked in Hungary using a 76 centimeter, so it's about 3/4 of a meter dish on the 3 centimeter band. And I can go on and show other things. This is a station with 2 Yagis in Taiwan. China is, by the way, quite active on EME. The Chinese have realized the importance of technology, and that amateur radio is a good way to get technology among their citizens. So now there's a lot of microwave and higher frequency amateur radio work being done by the Chinese, which didn't happen before. And EME, as I say, is a fascinating propagation. I'm giving a lot of details here that make why, if something's too easy, there's no point in doing it, right? So, but it's not that easy. There are things you've got to know, there's tricks you have to apply and learn. When you bounce signal off the moon, you run into what's called Doppler. Everyone knows about the train whistle. You're a train go by, the frequency of the whistle changes. The same thing when you bounce a signal off the satellite or the moon. Its frequency changes. So you got to be able to correct and take care of Doppler shift. You got to understand the effects of sky noise in the background. You don't want to operate in the middle of the Milky Way because there's a lot of noisy stars over there when the moon is there. At certain frequencies, there's Faraday rotation, which means the polarization of your signal. I don't have a good way of illustrating this, but it's rotated when you go through the atmosphere. Effect discovered by Faraday. There is lunar librations, which now people are smart, they calculate. This means that depending on the angles and the way the moon is moving, you get less of this variation, the signal off the moon. It's called librations through the rocking of the moon. The moon rocks. It's not obvious. You look at the orbit of the Earth and the moon is actually rocking. And that rocking only takes a little bit because of the moon's surface is not smooth. And that changes the signal that comes back to you. And so you want to operate, if you can, where the vibration effect is as slow as possible. So your signal doesn't get all broken up. So this brings me to the end, and the key points that I wanted to make here, that EME is challenging, but all you need is a Yagi or a small dish if you're an amateur radio operator. If you're not a radio amateur, or you need to get your license, and then you can do this relatively easy. All you need is your tech license for these frequencies, and you can still be a big gun, as they say. It's pretty easy with big stations, but there's still a lot to it. And I just illustrate some of the things I was saying before: accurate frequency, time. You got to be able to point your antenna at the moon. You got to consider the Doppler effect. You got to consider polarization effects. They all enter into the playing the game. So you gotta besides the rules, you got to understand how to apply the rules to be effective. With a weak station, all the above plus must understand how to use using digital technology, understand the limits of the digital technology that you're using, and you can go further. And there's the rest of this is more technical. This is just a frequency I'm telling people to operate on. I do a newsletter for people to bounce radio signals off the moon at the higher frequencies. And that means 432 or 70 centimeters and above. I do this newsletter, been doing it for almost 50 years. And that's just the link to it. If anyone emails me, I'd be happy to send it. You can just do a search on my call letters in EME, and you can find the newsletter. It has its own page where it's kept. And I'm going to stop here.
0.07.
Excuse me?
There is one item called activity, which is 0.07.
Yes. If you go to a particular frequency band, a lot of the digital activity is centered on 70 kilohertz above the frequency. So this would be, could be 144.070, it could be 432.070 kilohertz, etc. It's really that first 100 kilohertz of frequency, because you can operate over a very narrow bandwidth and people will spread out, but that's kind of like where you don't know if you're on there, you don't know if anyone's going to be on or anything, you look at 07. Question, now your question was on the lunar lander.
Yes, and we get signals from it and explain it.
Well, the lunar lander, I don't think is operational right now. It was, but when they left the module on I'm trying to remember the things they left on the moon. They didn't leave the lunar lander went back up, but they did leave some interesting items on the moon that help communications. They offered these boxes on the moon. I don't miss the keynote. Because we don't, it's really going to be a great keynote here. But when you have a signal goes up to the moon and it reflects from the moon, they have these types of triangular types of boxes. It's very interesting. Any signal that comes, it's this three-dimensional box, and it's reflected from it's reflected back in the same direction. So if you're, they were designed for lasers. So if you send the laser up to the moon, you can, if you have a high power laser and you hit one of these reflectors that are on the moon, you can make very accurate measurements the time it takes to send the laser signal up there. And those are still present and working on the moon. I don't know, there's an interest in putting transmitters, repeaters on the moon itself, but I don't know of any repeaters on the moon right now that are currently working. I had someone call me up not that long ago who was interested in putting a repeater on the moon. He was very excited. His son was interested in
Has that
doing
been
this.
done before? Did they actually have a repeater signal?
No, there was a fellow who's since passed away, Nick Marshall, W6OLO, who tried this whole project Moonlight, and he tried to get funding to put a repeater on the moon itself. You know, there's a lot we've done. We don't have time. I'd love to sit here and talk about satellites and like you probably have never heard of the Lagrange. Has anyone heard of the Lagrange? Oh, so we got a few people. Most of you do not know what Lagrange points are. Those are points that are equal gravity. They're stable points. You go to the Lagrange point, you stay there. And there are a bunch of Lagrange points around the Earth. And you put stuff. Space junk accumulates in the Lagrange points. And so those are spots where you put repeaters on the Lagrange points.
Our latest telescope was that.
Yes, it's in the Lagrange. Yeah. I don't know myself either. So they're all these interesting things. There's tremendous. I can talk about anomalies here. You know, you want to hear things evil, like things that you can't explain. When back in I think it was Apollo 13, we had a group of us, a bunch of students from TCNJ, and we set up to receive the Apollo astronauts. And they went around. This was Apollo 13, so quite a few years ago, more than 25 years ago. And we set up a dish. Full life lost the clothesline for a while, so we threw the clothesline down and we put the dish on top of her clothesline with ropes.
How much management?
Don't forget that.
I'm gonna make the beans up, right? And we put this dish up there, and we're using clotheslines to record my basement for ones. And we're watching this, and this is true. And one day we picked up, we could actually hear the astronauts. They had this S-band system, and they use subbands. So each subband has different types of telemetry and information, and the voice channel, you tune to that subband, and you can hear the voice of the astronaut. So there's It's an astronaut. We had a little display so we see the spectral term. And we're sitting there all of a sudden, and all these subbands, which are, they're visible, but they're not used. They all go up just like this. They went up off the screen of the adapter that we were using at that particular time. They stayed up there for about a minute, okay, or two. It's not very long. And then they slowly down. And we don't know how, what, we don't understand the physics, none of us, of what could have caused that signal. And this was the lunar orbiter we were listening to at the time. What would have caused that signal to go up? It went up 20, 30 dB in terms of decibels of power 10. It's got 1,000 times stronger.
Do you know anything that could have caused it? Like, do you have any?
I don't have any answer. We thought about, does something have documented, reflected the signal? We've asked, we sent that information to NASA. Never got an answer as to what could have caused that. But there are a bunch of people. It wasn't just me. There were we must have about 7 people there that saw this happen. And that's one of the things that I've seen that I have no explanation of. And there's no question that it physically happened. It wasn't something like a wire got there or something that it really happened. There's a lot of strange things still happening, but we can't explain. I think I should end this now from a time point. We want to make sure we get to the keynote. After the keynote, we're going to have a interactive forum. We're going to bring out what's left of our refreshments out there, so you get something to eat if you're staying for the banquet. But you're welcome. You don't have to go to the banquet to stay there. We're going to run an interactive forum for people that are here. We're going to talk about electric cars and get everyone, let them have their 2 cents. There's a lot of different opinions on cars, and a lot of the people in the audience have strong opinions. They have different directions than just our speakers. They listen to the speakers, so we're going to give everyone a chance to get involved and express their opinions at that time. Thank you.
Thank you.